Testing forcewell. Okay, in this particular video here, I'd like to show you what is behind the movie called Forcewell, which you can find in the Newton's Law 1 chapter. What this movie is about is allowing you to test your understanding of how an applied force on an object will affect that object's velocity vector, which is a very important aspect of this section of our class. So just a quick tour of the code before we begin here. In particular, you see the usual starting, the physics.inc, the cam, and the light source. You don't really need to mess with those. Then what you see is a couple of preset initial position and velocity vectors for you. So the ball is going to start at x equals minus 740 with a vx of 5 and a vy and a vz of 0. So you cannot change these. These are sort of a requirement of the program. Just leave them as is. Don't want you changing those. Bunch of usual stuff in here, the dt and the x time. And here's our mass parameter defined, which may be the first time this quarter we've used this parameter. So I'm sort of defining my object to have a mass of 1. And then here's the while loop, and it looks like I have a 0 net force on the object. And here's my key Newton's law that we want you to start getting into and trusting now that A is F over m, or the sum of the forces divided by m. Then if I go down a bit, I am drawing a red sphere once again, drawing the velocity vector, the force vector on the object. And if I go down a bit more, there's some other lines which are not allowed to change. They draw something called a maze here. So don't touch anything between these lines here. These are just something that are part of the framework I'm giving you to test your understanding of how a force affects a velocity vector. So leave all that stuff alone. So what will happen if I just render this movie outright is I'll get the following here. I'll see a red ball here with a big velocity vector sticking out of it going over towards the right. That's the initial position and velocity which I've set for you, which are not allowed to change. This brown structure here is a maze, and this green bar down here is, well, a part of the maze also. And what your job is in this particular movie here is to get the ball to go through the maze, has to travel through the maze like this, go all the way down, turn this corner, go down here and just barely touch this green bar, turn around, come back up again, go back around the corner and go back out through this star as it leaves the screen. That's what your job is. So you have a velocity vector on the ball. Now you have to start thinking about what forces would you apply to this ball to cause this to happen. That's the goal of this movie. Again, it's a force-velocity interaction exercise for you. How are you going to pull this off? Well, if I let the movie begin to render like this, I'll see that the ball keeps going to the right, and I have a time variable up here. This is how many times in the movie has elapsed at the current frame that we're examining. So we'll just watch that for a minute. And when the ball gets to about here, let's see what time that corresponds to. About 0.89 seconds or so. 0.89 or 0.9 seconds. I'll try to remember that. 0.9 seconds. My frames have stopped now, but it looks like at about 0.9 seconds, I would like to start to negotiate this turn now. And if I'm sort of thinking about how this velocity vector would be turned so it can start going down, I'm just going to guess that that means the force should be pointing something like straight down. Okay, so let's see about that. So if I want this velocity vector to start coming down this way, I need to put a downwards force on it right about 0.9 seconds. So I'll go back to the code and it says, look, okay, in the absence of any other logic here, there will always be 0 force on the ball. That's by design. Now, if it says insert your if statement starting below this line, what I'll do is I need to apply a force on the ball if the time is greater than or equal to 0.9 seconds. 0.9 seconds. Okay, that's sort of what I observed the movie. I thought, well, I better start turning at about 0.9 seconds. And that time that is elapsing on the screen there, and those little gray numbers, are this x time variable. We referred to x time a few times in the class, and what it is the global movie time. Like if there was a clock on the wall somewhere in the movie, it would read x time. We don't use it very much, but it's useful for this because if 0.9 seconds have gone by, what I'd like to do is I'd like to put a downwards force on the ball. I'll say that, so a downwards force is 0 along x, say minus 10 newtons along y, and 0 along z, something like that. Don't forget the semicolon at the end. These declare statements are the only statements in Power that always need that semicolon at the end so the computer knows when to stop doing this equating for you or assigning for you. And I'll put my matching end statement in there as well. So what I have now is a small modification as the ball moves. I'll assume I want 0 force on it, as indicated by this line right here, unless x time becomes greater than 0.9, then I want to put a downwards force on it to begin negotiating that turn. So with this, let's watch and see what I have now. So here goes the ball, sort of zinging along, and I think the 0.9 seconds was right about this region, right about here. And if everything goes well, I should see a big force vector sticking out of it, and hopefully it'll start steering that velocity vector around that turn. Here we go, right about there. There's my force vector right there, coming around. My frame stopped again. Yours will continue. You might have to set your frame to something like 200 or so as instructed in the instructions for this problem here. But with this big force vector coming out right here, I am seeing the velocity vector start to turn around this curve. So it looks like I'm on my way to getting this ball to turn around this corner to go start heading down towards this green bar. And keep in mind, one of the requirements that as we grade is you're not allowed to let your ball touch these brown borders at all. Think of these brown borders as like 10 million volts, and you'll electrocute and burn up your ball if that happens. And remember, your goal is to just barely gingerly touch this green one here and turn back around. Just by a couple pixels of overlap is about all we'll allow. Furthermore, it looks like the vectors are a bit long in here, and it's sort of irritating the way the letters start going off the screen. That's okay. What I can do is just come down here, and there's a statement we have available. You can read about it in the How Do I section of my book called Set Vector Scale. And if I just give it a number like 0.5 or something, that'll cut all the vectors, the lengths in half. It'll rescale all of them in half, and it'll make for a bit nicer movie. I will just experiment a bit more, because one thing that I've noticed sometimes also about turning that corner in the first corner of the movie is sometimes it is still going a little too fast, and it'll swing out and hit that far wall. So I'm just going to go ahead and apply a little bit of slowdown. So here's just a more interesting force now. It has -5 components along the x-axis, so it's actually going to point a component of the force over to the left and down, and see what that does now. So now when the ball hits about 0.9 here, I'll see a force vector that sort of points down this way like that. So we'll slow it down a little bit as it approaches this far wall here, but also get that turn going. So let's just see what happens now. I'm about to end the video then. I think you get the point now, and I'll give you just a few more words of advice. It looks like the vector is a bit shorter now. Here comes my force vector. Yeah, see, there it goes, half as long, pointing that way. And of course my frame's run out again, but now the ball is going to make this turn, and there's a component of force going that way, which will hopefully slow it down. So what is your job now? Well, you have to run more frames and observe just how well or how poorly it makes this turn here. And you have to keep your eye on this clock here and just sort of realize, well, what other force would you need to sort of maintain its trajectory? So it looks like the turn is fine, but you might need something else to get it away from a wall or slow it down or something. All you have to do in this picture movie is observe those times and keep piling on if statements. So say maybe after a bit more time goes up by, maybe after X time is greater than or equal to maybe 1.5 seconds, something like that, according to your observation of the clock. Maybe you need a force that's in some other direction. I don't know what. I'll just say, whatever you think, so much in X, so much along Y, and so much along Z. You fill those numbers in yourself. But just remember to always put, if X time is greater than or equal to, put your declare statement, don't forget your semicolon, and make sure you put an end statement to pair off that if statement. So in eventuality, what you'll have is just a whole series of if statements like this, and maybe after some more time that goes by, you'll have another if statement down here. You might have 10 of these by the time the movie's done. Turn the corner, gingerly touch that green bar, and go back up again. And these times will get successively greater. So that's 0.9, this will be 1.5, and so maybe this will be high as 2 or something like that. And if you look at the logic, does it all work? Yeah, if you pile them on in sequential sort of chronological time order, it should work okay. We'll always have a 0 force default. If we say nothing, just put 0 force on the ball. And if it's greater than 0.9, it'll assign this force. But if it's greater than 1.5, it'll assign this force. So 1.5 is greater or equal to 1.5 and 0.9. So yeah, it'll trigger both if statements. It'll do this one first and then do this one. But the point is that the ultimate force is only the last one the computer assigns, which will be the one that gets captured in this if statement right here. This one will get skipped because if time is about 1.5, it's not greater than 2. This one will get skipped. And this last force that's assigned is the last one that get routed into this line right here for linking to acceleration, then on into your physics equations. So that's the goal of the movie. Go around that turn, gingerly touch that green bar, and come back out and pass through the star. Good luck. Happy driving.